Hello, students. My name is Professor Jong-won Kim at the Department of Mechanical Engineering of Seoul National University. Now, this lecture is the last lecture on product drawing principles, and so today's lecture I'm going to explain the surface roughness, and then lastly the whole schematics for product drawings. Okay. So the use and importance of surface roughness is that it indicates how smooth the surface should be. So, of course, since the surface roughness, the word itself of surface roughness, it means that the smoothness of the surface. But more important is that it indicates the surfaces to be machined. Surfaces to be machined out of those which remain as original surfaces. Since I explained you before, this is the part before machining. All corner. This is a workpiece generated by using the casting technology, something like that. So all surfaces are smooth, but since considering the function of this part, some part of the workpieces has to be machined like this. So, in this case, for the surface to be machined, the degree of smoothness is designated, and surface roughness becomes and then the surface roughness becomes better as it is machined more accurately, right? So this is the use. This is the main use of surface roughness in the product drawing. And types of there are some types of surface roughness. So the mostly used surface roughness is the arithmetical mean roughness, which call it RA, since the A is here. And two surface roughnesses used instead of RA is RY and RZ. So RY is maximum height roughness, and RZ is 10-point mean roughness, which is about four times larger than the RA. And sometimes RY and RG are used in some cases, but if you want to know the meaning of RY and RG, please refer to the other text. But usually RA is frequently used, so don't worry about it. And the others that have been added recently is SM and S and TP. So these are definition of surface roughnesses which are added recently to the standard. So maybe since I'm old generation, so I didn't use any SMS or TP, the newly defined surface roughness. But since you are the new generation engineers, maybe you are going to use one of these in later times. But at the time, please refer to the other textbook, please. Anyway, it's true that RA surface roughness is mostly used in the industry. And so terminology related to surface roughness is that when you have the roughness tester, then you have proof, and proof is Proof is touch it on the surface where which surface you are going to measure. You want to measure the surface roughness. Proof, and then you get some graph like this. So which is zoom out, and the curve, you have such a curve, which we call a section curve, okay, and okay. So, but surface roughness is mainly focused on the high frequency shape, not low frequency shape, right? So using a filter, you eliminate the low frequency part to obtain the roughness curve. This is the roughness curve where the low frequency curve is filtered out. So this is the roughness curve, and when you try to measure the surface roughness of the specific plane, then you just understand that they are defined. The roughness width is defined L, large L. So only in the roughness width L you measure the surface roughness. So if you zoom out the curve within the length of L, then you can find a curve like this, and we call it. And there is an average line. There is average line exists. The average line is the line which makes the upper part and under part be equal, right? And that is the average line, and we call it the above of average line. We call it peak, and the under part we call it valley, and this is. The peak line is the tangential line parallel to the average line, and which is a peak line, and valley line is the line which is tangent to the roughness curve, but it is below the average line. Okay. And the definition of arithmetic mean roughness RA is here. So sample only the roughness curve portion L, curve L, the roughness width L from the whole roughness curve, and express it by the function y equal fx. Okay, so this is y-axis and x-axis. So this is the function represented by the function fx. And then the definition is the integration of the absolute value of fx. So it means the absolute value of fx is like this, which the curve is all above average line. And then this is the average of at the length of L. So divided by length L, then you can get the value RA in micron, in unit in micron. The value obtained from the above formula in micron is the arithmetic mean roughness. Okay, you got it? So then we have to select the RA value. Since as the final RA value, you have to select a number from the below series of numbers. Only these numbers, which is barely larger than the value obtained in micron unit from the following formula. So it means that if you from the plane which you like to measure the surface roughness within the length L, you can get many RA value from the function from the equation like this RA. So maybe those RA numbers may be 1.2 micron, the other is 1.3, the other is 1.2, the other is 1.4. Then all numbers are, that is 1.6 is very larger than those values, 1.2, 1.4, 1.3, right? Then the surface roughness of the plane you like to measure the surface roughness. We call it, the surface roughness is 1.6 RA, 1.6 micron RA, okay? So RA values are selected from only these numbers, okay? If you get the, at calculation, you got it 1.25 micron, then 1.6 is your RA value. If you get the value of 0.3, then the RA value is 0.4 micron. Okay, so RA values are selected only from these numbers, only from numbers. All right. So there is no 2.8 micron RA value. No, 2.8. Then you have to call it 3.2 micron RA. All right. Okay. And we call it 1.6 micron RA surface roughness. Okay. All right. And the RA range obtained by each manufacturing process is like this. So maybe, I don't know, you know, the process grinding. So the grinding, the typical symbols is G. I don't know if you ever used lace turning, so which the symbol is L, large L, milling, large M, okay? Super finishing, GSP. This is a standard symbol which represents corresponding manufacturing process. So maybe grinding is using some grinding field. So maybe it is after grinding you can get some very smooth surface, which looks like surface of the knife, maybe knife. Then the RA value is around 1.6 micron RA grinding, and the lace and milling, you can generally you could get 6.3 RA micron RA roughness. Maybe mirror surface. You can get the image of yourself from the mirror. That means that surface is very, very smooth, and surface roughness is 0.1 micron. 0.1 micron. Your diameter of your hair maybe 20 micron or 30 micron. So 0.1 micron is the 200. You divide your hair by 200 pieces, then the length is 0.1 micron. So it's very, very tiny length. So surface roughness, RA. You remember the definition of RA, right? Integration of absolute value of effects. Then you can get the value RA value 0.1 micron. That's roughness. Imagine that, right? That is the surface roughness of mirror surface. Okay, and this is a surface texture symbol. So symbol is something like this, something like the triangle, and you have a line here. So 6.3, and if it indicates the bottom surface, then it has turned 180 degrees. So the direction is like this. So this is surface texture symbol. It means that the original material surface has to be eliminated by machining until its surface roughness becomes 6.3 micron RA. Maybe the manufacturing process is like a milling process, right? The number 6.3 means the upper bound of the surface roughness RA required for that surface, and its unit is micron. So 6.3 means the upper bound of the surface roughness. Okay, so if you measure the surface, if you measure the surface roughness within length L in everywhere, L within the length L, every part of L of the upper plane, you try to measure the surface roughness using the tester, then if you can get all values, it should be less than 6.3. So 6.3 is upper bound, right? So that is the definition of a surface roughness. So to place the surface roughness in your drawing, you are using the technique like this. So surface roughness, this means surface roughness, and you see a symbol 6.3 here, and in the curve you have a 3.2 and 0.8 and G. G means the grinding process, G, and it means that center through hole here, 0.8 and grinding. 0.8 micron RA. The grinding process is indicated specifically as its machining process, right? So center through hole, the surface of center through hole 0.8 micron RA, and both end plane is 3.2 and 3.2. So 3.2 micron RA. No specific machining process is indicated. So you may use the milling or grinding. It depends on you. Okay, and notice the direction of the line, upper surface, and this is 90 degree turned to the left. Also 90 degree turned to the left, and 90 degree turned to the left. So please notice the direction of the line, which is extended from the triangle. Okay, and then what's the meaning of 6.3? That means except for 3.2 micron and 0.8 micron with grinding, except for two surface roughnesses, 3.2 and 0.8, the other surfaces are machined as 6.3. So 6.3 is not indicated in this drawing, right? This is the very useful way of placing surface roughness. So except for two surface roughnesses, the other surfaces are machined as 6.3 micron RA. This is a very nice technique. Another cases are here. So if the same RA symbol, in case that many surfaces own same surface roughness, okay? So if the same RA symbols are marked on many surfaces, the drawing becomes complicated. So this means that except for 0.8 micron and 3.2 micron, except for, which is in the two curves, the other surfaces are machined as 6.3. Okay. In drawing, there are no 6.3 roughness indicated, but the drawing, it means what? It means except for 0.8 and 3.2, except for 3.2 and 0.8, the other surfaces are machined as 6.3. Very useful way. Yeah, this is what 6.3, and in the drawing there is no 6.3. But what it means what? All surfaces are machined as the surface with its surface roughness 6.3, right? Okay. So this is a very, very useful way of placing surface roughness, all right? Okay, in case then many surfaces on same surface roughnesses, please use this technique, all right? Okay. Now, since this is the practical part drawing where the auxiliary view is applied. which I explained it at the previous slide when I explained auxiliary review. Now, you see, this is a real part drawing which I generated when I executed the project of development of a special machine tool. And at the time, yeah, of course, the title space is not shown in detail, but in title space, you have to add the general tolerance and also the symbol of indicating third angle projection. All right. Now look at it. Surface roughness, 6.3, and in the curve you have 6.3 grinding, 1.6, and 1.6 grinding. Now let's look for three surface roughness. Now 6.3 and G. Where is it? Now yeah, here. 6.3 and G. 6.3 and G. Now, where is it? Yeah, here, 6.3 G. Okay, right. And what about 1.6 without indicating any machining process? 1.6. 1.6 here, 1.6, 1.6 and 1.6, and 1.6. 1.6 RA using grinding process. Where is it? Where is it? Oh, where is it? Let me say 1.6. Here, 1.6 and grinding. So this surface, the surface of this cylinder, whose diameter is pi 40, the surface should be 1.6 with grinding, right? And then the other surfaces, all the other surfaces which is not indicated specifically should be machined with the surface roughness of 6.3. Okay, you got it? Now it's very clear plating of surface roughness here. And also the note is very important. Note, C.5 for all edges if it is not indicated. So C 0.5, this note is very important. Without this note, then all edge remains as a sharp edge, right? It's like a knife edge. So it means that with this note, C means cornering, right? So C.5 with this note, all edge should be machined additionally. So it should not remain as sharp edge. So it's very important, this note. If it is not indicated, so some edge C 1.5 edge cornering, see, right? C 1. Especially indicated. Okay, right? And now you see the geometric tolerance here. And what about dimensional tolerance? Pi 40 JS. JS, you try to find it, the meaning of JS in the dimensional tolerance in the table. JS is usually plus minus pattern, plus minus what? Something pattern, plus minus JS. And also dimensional tolerance. Now, yeah, look at it. Pi 80 H7. Okay, dimensional tolerance. All right, and what about geometric tolerance? Now, datum A is attached to the pi 40. So A means datum A is the axis of pi 40 cylinder axis. Now the perpendicularity of this surface. So it means this surface, the axis A is the axis of this cylinder. So the perpendicularity of this surface with the axis datum A should be 0.01 millimeter, right? Okay, and what about B? B is what? B is attached to the pi 80. So B is the axis of pi 80 cylinder. So this is in vertical direction. So this axis, B. B and A. B and A. A is here. So A and B are perpendicular each other. And that perpendicularity should be 0.01 millimeter. Okay. Right. It's all, and now perpendicularity of this surface to B is what? B is this axis, and this perpendicularity 0.01. Now, see? So all geometric tolerance, dimensional tolerance, and surface roughness all added, and it make a very, very excellent practical part drawing. Okay, please take it as your example. Okay, now this is the final chapter. So I'm going to explain how to make product drawing, which consists of assembly drawing and part drawing. And so this is the all summarization of the principles of product drawing, right? Okay. Now if you develop a new product, then you have to know that there are several types of parts. So they are classified according to its source. Source means that the first one is M part. We call it M part. M is the abbreviation of manufacturing. So M part is manufactured inside the company own manufacturing facilities, because these M parts are very, very important part. So if you ask some company other than outside company, then sometimes you may lose control of production. For example, if you are a designer at Hyundai Motor Company, then, for example, the car body, or engine block, crankshaft, transmission case, these parts are very important, right? So, so the car body is main part of the automobile. So if you ask the outside company to manufacture your car body for you, then sometimes you cannot control the technology or the or production plan. So it is very essential that Hyundai Motor Company must manufacture car body, engine block inside the company by using the company own manufacturing facilities, right? So these parts, we call it M part. O part is O is abbreviation of outside. So so relatively the parts are not that essential or important. And if it is manufactured inside the company, then sometimes the investment is enormous, and you may lose economical merit. So in this case, you order the outside company to manufacture it. For example, ABS, bumpers, back mirror, seats. Those parts are belong to O part. Okay, and the last one is P part. P is abbreviation of purchase. So P part, these parts are element parts listed in the standard specification, like Korea standard or ISO, or it is listed in the brochure of the outside company brochure. For example, bolt, nut, bearing, springs. Okay, that are the element parts. So the drawings are already listed in the brochure or Korea standard. So these are the purchase part. Okay, and drawings. So drawings which you have to newly make when you develop a new product is the assembly drawing and part drawing. So assembly drawing shows the whole structure of a product and also required parts. And part drawing must be made for each M part and O part. Okay, so for P part, the purchase part, you do not need to make any part drawing, since there are drawings already in Korea standard or brochures in the company. Okay, in the company which provide the purchase part for you. So, but however, the outer shape of P part have to be drawn in the assembly drawing. So it's assembly drawing, the shape of bolt and nut, spring, bearing are included. So even if for P part, you do not need to make any part drawing for it, but in assembly drawing, the shape of every P part have to be drawn in the assembly drawing. Okay, all right. And also you have to understand the structure of the product drawing. So, and there are several layers of levels, like the social structure. So, and a assembly drawing owns several assembly drawings and parts drawings. For example, let's see in level 0, the most upper level, level 0, this is an example of assembly drawing for automobile. Let's assume that you are developing a new product, new automobile. Then level 0, the first very important drawing is the assembly drawing of whole automobile. Okay, whole automobile. All right. Then in level 1, just below level now you see these are the abbreviation of assembly. So in shop floor, in industry, many employees in the company, they call it ASI, sometimes ASI. It is abbreviation of assembly. So most people say ASI drawing, all right? Anyway, and so level 1, there are many assembly drawing, ASI drawing, maybe, assembly drawings and parts drawings. It means that according to engine ASI drawing, assembly drawing, maybe the engine unit, you may bring engine unit, right? And transmission ASI drawing, you have assembly unit, transmission unit. And in such a way, for airbag ASI drawing, your airbag is here. So there are many units. According to the level 1 assembly drawing, you have engine unit, transmission unit, airbag unit, so many units here. And according to part drawing of level 1, the part drawing maybe car body part drawing for car body. So car body is here, and maybe according to the other part drawing, you have a part are here, many parts, and many units are in front of you. Then, and also in the assembly drawing at level 0, there are many P parts. Purchase parts are listed. So according to that list of purchase parts, you have a purchase part here. Okay, for bolt and nut, bearings. Okay, purchase parts, bolt and bearing, nut, and according to part drawing at level 1, many parts, and also assembly drawing at level 1, you have an engine unit, so many units. Then, using that units and parts and purchase parts, you can assemble one automobile, right? Okay. Now, in same way, for example, engine assembly drawing has so many assembly drawings and parts drawings at level 2. Okay, engine assembly drawing level 1. So in level 2, according to the assembly drawing at level 2, you have a fuel injection unit and fuel filter unit, many units. And according to the part drawing at level 2, you have many parts. Okay, and also in engine assembly drawing, there are lists. In assembly drawing has the list. I'm going to explain it later slide. Okay. In engine assembly drawing, there are P part list in the assembly drawing. So according to the list of P parts, you have purchase part. Now, purchase part and parts, there are many parts according to the parts drawing at level 2, and according to the assembly drawing, you have a fuel injection unit and fuel filter unit. Then you can assemble an engine. Okay. All right. Okay. In the same way, transmission assembly drawing, also it has assembly drawing, many assembly drawing and parts drawing, and purchase part is listed in the transmission side drawing. Okay. All right. So in this way, there are level 3 too. In level 3, okay, level 3, level 4, level 5, level 7. Okay. In this huge structure of part drawing, that is huge structure of part drawing. That maybe the number of drawings, assembly drawing and part drawing, maybe the number maybe over 20,000 or 30,000. Okay. That huge number of assembly drawing and part drawing, then now the development of new automobile, that procedure is finished. Now we are ready for mass production. Okay. Now imagine that huge number of drawings. Okay. Right. You have to generate that huge number of drawings, parts drawings, and we call it a set of product drawings. All right. So please imagine that to develop a new product is a very, very great project, especially in the sense of product drawing, making product drawing. Right? Okay. All right. Now, yes. So the lowest level, the assembly drawing owns only part drawing, right? Now, okay. If it is repeated, then the lowest level, there is no more assembly drawing exists. So now only part drawing. Then the level of level of product drawing finished. So, as an example of the structure of the part drawing, let's see that let's assume that the structure of the part drawing of transmission X is like here, like this. So this is a level zero transmission X assembly drawing. So and transmission X has in level 1 a pulley unit assembly drawing and power unit assembly drawing and 4 part drawing. Okay, so it means that according to 4 part drawings, there are 4 parts and power unit. Okay, and pulley unit is here, and an assembly drawing listed in the assembly drawing for transmission X. Purchase part here, then you can assemble transmission X. So, and now looking at the pulley unit assembly drawing, level 1, pulley unit assembly drawing has part drawing, 4 part drawings, no assembly drawing, only 4 part drawing. Then there is no more level 3 for pulley unit. Okay, since in level 2 there is no assembly drawing, only parts drawing. So it ends at level 2. For power unit assembly drawing, it has 1 coupling assembly drawing and parts drawing. Okay, so coupling assembly drawing has 4 parts drawing at level 3. So in this structure, you can see that transmission X, the level is at level 3, the structure of the product drawing ends. Okay, right? And transmission X, it has 3 assembly drawing, and also and 4 and 4 and 4 and 4, so 12 parts drawings. Okay, so transmission X, so relatively small scale of the structure of the part drawing. Okay, now I will give you one example of one assembly drawing and 4 parts drawings for pulley unit assembly. Okay, pulley unit. So I will show you the structure of the pulley unit is here. So the function of the pulley unit is to transfer a spinning motion of pulley to shaft. So pulley is here, pulley 3, number 3, pulley 3. You please notice the number is attached to each part. So number 3 to part. This number will be used in the assembly drawing when you make assembly drawing for this pulley unit. Okay, so number 3 is attached to the pulley. The pulley, actually, the pulley, it is not seen in this drawing, but there is a belt. Belt is belt is around this pulley. So belt is spinning actually. According to the motion of the belt, the pulley is rotating, spinning. Okay, then that spin motion of the pulley is transferred to this shaft. Okay, shaft is also spinning. So the okay, so 4. The part is 4. The shaft is 4, number 4. So since the shaft is supported by 2 bearings, 6 is attached to the bearing. So 2 bearings. Okay, so 2 bearings support both ends of shaft. Okay, all right. Now, the pulley and shaft is combined, joined by using this nut and washer. Okay, right. Pulley 3 is fixed on shaft by bearing ring, nut, and washer. Okay? And key transfers, key, now key. Please remember when I explained to you the function of key, okay? Please remember that. So key transfers motion of pulley thread to shaft, okay? It do not depending on any friction, key. The key transfers motion of pulley to shaft very, very positively without depending on any friction. Key. And oil seals 9 and 10 are assembled to prevent dirt coming inside the shaft from outside to inside. The dirt should not get in. So the oil seals are prevent. The function of oil seals is to prevent any dirt coming inside the shaft. And cover 2 is fixed by bolt 15, and loosening is prevented by a special washer 14. Okay, all right. Now, this is assembly drawing of pulley unit. Okay, now assembly drawing. The first step of making assembly drawing is to describe shape, and it is done mostly by the sectional view. Okay, sectional view, you see? The front view, but it is all sectional view. Okay, shaft, bearing, bolt is not drawn. The hatching is not given to the shaft bearing. Okay, hatching. If your hatching line is inside the shaft, then it makes very huge confusion. So the shaft, even if shaft is drawn in the sectional view, the hatching is not done. Very important. Bearing too, no hatching. Okay, and bolt no hatching, never. Okay. Anyway, this is what? This is a support. Support, no hatching. Please remember that. Okay. All right. So, since actually the assembly drawing, it tried to show the structure of the part joining inside the product. So sectional view is very, very natural. Okay. Without using sectional view, then how can you express the joining structure of your product? So sectional view is very important. Anyway, okay, so this is the front view, and this is the left side view, and since it is symmetric, so using the center line, only the left part is drawn. And second step is to place major dimensions only, width, height, and depth. That's enough. Never try to give every dimension, every detailed dimension. Assembly drawing, you don't need to place the detailed dimensions. Only major dimensions are enough. Okay? Width, height, depth information only. And third step is very important. The list of required parts should be here. This is the very, very essential part of assembly drawing. List of required parts. Okay. I will explain it in detail in the next slide. So please wait. And then fill out the title space. Okay. So part name, assembly, assign, and pulley unit, and group. It belongs to assign transmission X. So it's here. And quantity 1. 1 pulley unit assembly for transmission X. Okay, so quantity 1. And the drawing ID is here. What is it? BU, BU, why BU? Maybe, anyway, BU is a symbol for presenting your product. So BU and 100. Okay. So the ID of assembly drawing is BU 100. So if here ID X, here is X is 1, so 100. Then the part drawing which belong to this assembly drawing, the part ID is assigned as BU 101, BU 102, BU 103, BU 104, BU 105. Okay, so this is a part drawing, 5 part drawings which belong to display unit assembly drawing. So since the part ID is 100 for the assembly drawing, so the parts which belong to this 100 assembly drawing, then the part ID is given 101, 102, 103, 104. Okay. If the assembly drawing, the assembly drawing ID is BU 200, then those parts which belong to the 200 assembly drawing 200, then part ID gives 201, 202, 203. This is the technique, the way of giving part ID in industry. So for example, if you see the part ID, part drawing, whose ID is BU 304, then you can easily know that, oh, this part belongs to the assembly drawing BU 300, right? So this is the way of giving a part ID in industry. So, okay, all right. Okay, so now the list of required parts are very important in assembly drawing. So this is list of required parts. So assign a number by a leader and list the part information per number. So assign a number by a leader. So for example, number one is attached to the pulley. Okay, number 1. So number 1 is here. Please note that I believe that you can see the number here in your slide. So please see number 1 is here, right? Number 1. Okay, you can follow me. Number 1 here. Now part ID BU 101 and name is body. Oh my God. Oh, body. Sorry. Oh, number one is here. Sorry. This is number 3. This is so small that I'm confused. So number 3 pulley. Here. Number 3 BU 103 pulley. Okay. Anyway, number one is here. So body and material. This is a abbreviation of material here. Material is GC20. GC20. This is the material symbol for cast iron. So the main body, the materials are made from the cast iron, GC20. So cast iron, and quantity 1. Okay. And 2 is cover, so 2 is here. 2 is here. Now this is 1 and this is 2. This is a cover. We use 102 and cover and material GC20. So cover is also, the material for cover is also made by casting iron. Okay. And number 3 as a pulley, also GC20. So okay. All right. And part ID use drawing number for M part. So M part is now from number 1 to number 5 is M part until the color. okay, BU105. So M part, drawing number, okay, and below color 6. For example, 6 is BRG 6003 bearing, okay, and material number 6003 and quantity 2, and Hankook is the company name. So this is for P part, build your own part ID system, okay? So bearing, snap ring, oil cell, key, and washer, hexagonal nut, washer, hexagonal bolt. Those P part, purchase part, since there is no part drawing, so no part drawing, so no drawing number. But you have to give each part a unique ID, since like a student ID. Okay, so every company has its own system for giving the unique ID to each purchase part, right? So don't worry about it. For the part ID for purchase part, if you enter the company, you will become an employee of the company, then the first step is to ask what's the system of giving part ID for each purchase part. All right? Okay, so don't worry about it. So for P part, build your own part ID system, or ask a company to give you to let you know the own part ID system. Okay, so don't worry about it. So material for P part, then it is the material is listed here. So GC20 for BU104 shaft SM45C. So this is a steel pipe. Okay, so that is a steel pipe SM45C. So that's a steel pipe. For P part, use nominal dimensions over specification. So for bearing, on the column of material, the number 6003 is listed, which is the specification of this bearing of the Hankook company. Okay. So in remarks, quantity required number of parts for each unit, and remarks maybe list the manufacturing company for P part. Hankook. Okay. The other hexagonal bolt, maybe so many manufacturers for bolt and nut, so you don't need to give the special company name here. This is a general standard element part. So, all right. The specification is here. Okay. Maybe these specs are from the Korea standard or something like this, or from the brochure of the company, maybe, right? Okay. Now, this is a part drawing of body, whose drawing number is BU101. So this part belongs to the assembly drawing, whose drawing ID is BU100, right? So now, okay, part drawing, yeah, describe shape, all right? So this is the front view, and this is the right side view, okay? And dimensioning, since it's a part drawing, all dimensions have to be placed. Dimensioning, okay, and dimensional tolerance, you see, H7, H8, you are familiar with this, okay, already, dimensional tolerance, and geometric tolerance, okay, class 8 for this part, class 8. So this part, the body, H7 and H8, the IT class, the accuracy. IT class for accuracy is around class 7 or class 8. Okay, So geometric tolerance also given based on the class 8, okay, which means that, for example, let me see. Now this is a datum A, which is the bottom surface, bottom plane of the of this part, and datum A. Now see here, what is this? A, and parallelism is how? Parallelism of point 0.05, so which is 50 micron. Parallelism 50 micron. Whose parallelism? Because this sign attached to the pi 35 H7, 35. So 35 is what? The inner cylindrical surface of whose diameter is pi 35. Okay, and actually this is axis of the cylinder whose diameter is 35. So axis. Okay, the parallelism of this axis, according to the datum A, is parallelism is 0.05, 50 micron. So 50 micron. Where 50? 50, number 50 micron come out from the class 8. Now, the dimension, the distance of the axis and bottom plane, the distance is around 66. Now look, 66. So 50 to 80, 66. And now class 8. So what is it? 46 micron. 46 micron. So that's why the parallelism is around 50 micron. Okay. So 50 micron, according to the dimension, nominal dimension 66, which is 66 is what? The distance of the axis and the bottom plane, 66. So parallelism of 0.05, which is 50 micron, according to the 66, is a class 8. Class 8. Geometric tolerance, class 8. Okay? You get me? Okay? Now, let's see the other geometric tolerance. Which is it? Now, datum B is the axis, and according to the datum B, here, datum B, the perpendicularity of this plane, this small plane, okay, the plane, this plane, and with the perpendicularity of this axis. Now, so what's the length of this axis? Is around 55. Now, so 55 is around 88. Class is 46, 46. So the parallelism, the perpendicularity is 0.05, 50 micron. Okay. So geometric tolerance, class 8. Okay. So all right, and tighter space, part name, body, group, the body belongs to a psi Pauli unit, okay, quantity 1, and weight should be given, even if the missing here, but material GC20, scale 1 to 1, and BU, drawing ID, BU 101, okay, approved by Jong-won Kim, drawn by Mr. Bae, and geometric, the general tolerance here. All right? Okay. All right. Okay. So parts drawing of cover, same story. BU 102, and since maybe this is something like ice hockey puck. Ice hockey. Do you remember? The first step is to select the front view. So since this part is similar to the ice hockey puck, so very thin cylinder. So this is the front view, and this is the right side view. Since it's fully symmetric, so only the left part of the cover is drawn here. Oh, then note is very important. If this is missing, then if since this note is missing, then you may generate very poor part drawing. So note, very important. R3 if it is not indicated. So since this is a cast iron material, so the cast iron, so the edge is very rounded. So the round is round R3 is the nominal dimension. C 0.5 after machining, right? So since you see the roughness here, roughness. So in 25 and 6.3 is specially designated. So you see here 6.3 surface roughness and 25, okay, given. So for only if the surface roughness is designated, then that surface must be machined. Okay, all right. So if the surface is not designated specially, then that surface remains as its own material surface. Okay, so this symbol indicates that the surface roughness just for its own material surface, no motion. Okay, right? So surface roughness important. All right. Okay. Now this is for pulley. So only one view drawing. Okay. All right. So full sectional view, and with the symbol of pi. Even if there is no side view, we understand that this is the cylindrical shape. So, all right. And surface roughness to note. Okay. Only the key groove, upper direction, and there are some F7 dimensional tolerance. Why F7? Don't worry about it. Just if you look at the standard for key groove, then you can get the dimensional tolerance F7 from the standard. So don't worry about it. Okay. All right. This is a very nice drawing, and this is shaft. Okay, part drawing for shaft. Okay, key groove here. Okay. All right. The metric thread here, very nice note. This is the 6.3 and 1.6 surface roughness. So only 1.6 is designated here. So 1.6. So the other surfaces which is not designated as 1.6, that surface is all must be machined with the surface roughness of 6.3. Okay, so this part has no material surface. All material surface has to be removed. Okay, all right. And this is the part drawing of color. So it's also one view drawing. Okay, very nice drawing. All right. This is interesting. Only 6.3 is designated, and the other surfaces are should be machined 1.6. More smooth surface comparing to the surface of 6.3. So, okay. Note C 0.5 after machining. Very important note. So all machined all edge, sharp edge must be smoothed. Okay, all right. Okay, so now I must tell you that even if I lecture all principles for making product drawing, but still I was, it was a few years ago, I was very, very disappointed with the part drawing which are made by one of graduate students in my department. Okay, the technicians who try to make this part called me that he made some mistake because of the part drawing which the graduate student submitted him. So he showed me, the technician showed me the part drawing, this part drawing. Then I was disappointed. This is you see, part drawing which is made by the automatic CAD expansion. So maybe that graduate students generate the 3D shape first, and by using the automatic CAD expansion, he made the part drawing like this. Okay. Now, since you got all class, my class, right? Then can you point out which are wrong? Can you point out that? This is very important. This is very important. Now, if you finish my lectures on the part drawing, product drawing, then you must point out the mistakes of this part drawing. Okay? This is very, very poor part drawing. Okay? If this is a language, then this is a language which cannot be understood by technicians in the field. Okay? Now, which is wrong? First of all, the title space. There is no third angle symbol, no general tolerance is given. Okay? Right? This is a very serious mistake. Very, very serious mistake. This is I think this is a F grade part drawing. F. Okay? Now, secondly, the shape description. Now, what is the first step to make a part drawing? First step is to select the proper front view. Now, the shape of this part is like a cola can, okay, Coke can, long cylinder. Then, which is the front view for long cylinder? Okay. Now, this is the front view, proper front view direction. Now, in this drawing, this is the front view, right side view, and left side view, and top view. This is a ridiculous. Okay. Now, front view, okay, and minimum number of views. These poor graduate students made all side view, left side view, and top view. Oh my God. Okay, and sectional view. This part has so many holes inside the part. So sectional view is a must. Okay, all hidden lines. The hidden features, the features inside the part cannot be seen very clearly. This is all hidden lines, right? And dimensioning, you know, since there is accumulation of general tolerance, even if general tolerance is not given here, though, accumulation of general tolerance. So reference dimension, very important. Which is the reference or which is not. Okay? And dimensional tolerance and geometric tolerance. Only the dimensional tolerance is E7, large E7. Actually, for the shaft, then it should be maybe the smaller letter, but this for graduate student use large E7. I don't understand. And E7, the tolerance, the dimensional tolerance of E7, maybe I don't remember that. Since I have so many experience in industry, but I never seen any E7 dimensional tolerance. Who is using E7? You know, it's a totally okay. In the dimensional tolerance, when I explained the fitting system, that there should be a table for combination of H7 and H7 and H tolerance and with the K. Okay, that combination is recommended. There is no E7, you know. Okay, and dimensioning of smaller, yeah, you see the symbol, this figure and 5 and this figure and 6. I never told you such symbols. Okay? Why this graduate student use this symbol? Who is not used in industry, you know? This is a ridiculous drawing. Please understand that. Okay? All right. So since this is a good example for part drawing, okay? Now, sectional view, nice sectional views. Yeah, E7, I was very reluctant to use E7, but since in original drawing he used E7, so just I copy it. But I'm very reluctant to use dimensional tolerance E7 though. Okay, the nice sectional views. So now you can understand very clearly what features are inside in the part. Okay, all right, dimensioning and. So please compare the drawing here and this. Okay? Please understand that by the automatic head expansion, do not give you the proper part drawing. Okay? Very important. Very important. Do not repeat this mistake. Okay? All right. So I wish that since you finish my lectures so far, so I wish that you make this type of drawing, professional drawing, in your future, in your job career, please. All right. So what's important? The all principles I discussed in this lecture, that's very important. Okay. Please believe me. Please believe me that those principles are very important. Since this is what I understood from my industry experience. Okay. All right. This is a final project. So please make a product drawing, which consisted of 1 assembly drawing and 5 part drawings. Okay, for crane pulley unit. So this is so 1 assembly drawing. You have to finish the 1 assembly drawing. Now I'm going to at the blackboard mode. I will show you the whole shape for this crane pulley unit. Okay. All right. Now this part is a plate, and this is the support. So this is a support. Okay, so in plate and 2 support, if it is assembled, then the shape is like this. Okay, now then the bushing bushing has to be inserted into two holes. So now after, if you inserted the bushing, then the shape will be like this. The bushing is the material is brass, so very low friction, so it is used as the sliding bearing. Okay, so now as the bush is assembled, then shape like will be like this. Okay, all right. Oh, this is a little large. So, this is a smaller, something like that. Okay. Now bushing is assembled, and now the shaft has to be. If the shaft is assembled, then it looks like this. Looks like this. The shaft is assembled. Okay, this is a bushing. This is a shaft. Now, the last one is a pulley. Okay, if it's a pulley is assembled, then the whole shape it would be like this pulley. So pulley is assembled. Then all detailed parts are gone. The shape is gone. Only the pulley is looked outside. The pulley is here. Okay. So this is a pulley. So. Okay. So it's like what it looks like. It's something like a wheel. Something like a wheel. Wheel for crane. You see, in the factory, if you're entering into the factory, then in overhead crane, there are so many overhead crane is moving. Above in the air, the crane is moving in the factory. That is a field for that crane. It's a field. Okay? So we call it crane pulley. Okay? All right? Okay. So the project is you have to finish the assembly drawing for the crane pulley. Okay? So crane pulley describe shape, and mostly by the sectional view, right? And major dimensions has to be placed, width and height and depth, and list of required parts. How many required parts it has? Okay? How many? In the drawing? 1 plate, 1 and 2 bushing. No. Pulley. Secondly, pulley. Third is support and shaft. And fifth is bushing. So 5 part drawing, 5. And 6, hexagonal bolt and washer. So 7 parts. So, right? So 1 to 5, the part drawing has to be made. And 6 and 3 are P parts only. So only 7 parts. All right? And fill out the tighter space. Okay? Now this is how to draw screws. Now I explained it in the previous lectures. So the thin line represents the thread. Okay? So now you have to assign dimensional tolerance on part drawings. So maybe shaft and pulley is a press fit, all right? So the pulley and shaft is a press fit. So maybe you are going to use hammer or press to make it if it is fit to make a fit system for fitting, then for press fit, if you achieve a press fit, then there is a combination of the recommended combination. So you have to use it. And bushing and support is a precise fit. So precise fit. Precise fit is what? You have to align two parts very carefully. Then you can assemble it by using hand. So there's a precise. Once it is assembled, then the disassemble, you need a certain level of force. Okay. Shaft and bushing loose fit, because it should be the relative motion should be possible, because the function of bushing is bearing. So shaft is turning inside the bushing, so loose fit has to be achieved. So, okay, and the other one is case by the dimensional tolerance has to be given case by case, but the height between two planes, this plane and this plane, has to be given. Okay, and please think about it. And geometric tolerance, the parallelism between the bottom plane, for the support, the bottom plane and the hole where the bushing is inserted, the parallelism has to be signed. So since you are going to apply ITA class to 48, the dimension 48 here, 48, then if you're looking at the table, then the 39 micron, so maybe parallelism of 0.04 millimeter may be given. This is a 40 micron. Okay, so same story. So bushings are concentricity of two cylindrical surfaces. So since the length is 19, so IT8, then looking at the number from the tables, 33 microns, so maybe concentricity of around 0.04 millimeter can be given. So same story. So in parallelism between two planes where support are fixed, in D, C, maybe parallelism of two bushing inserted surfaces, maybe the same story, same logic. Here you can give, you can select the proper geometric tolerance. Okay, and also finally the surface roughness should be given. So a part whose material is the GC20 iron cast, then only some portions are machined. So only the portions which must be machined, then surface roughness has to be given. Okay, right? And the upper part whose material is bronze or steel, then all surfaces are machined. There remains no original surface. In this case, I explained to you the way of giving surface roughness. So please remember that and try to make a perfect part drawing, please. Right? Okay. So I'm going to give you one example for bushing. Okay. Your project, I show you a part drawing for bushing. Please remember. Please see. Note. Okay. I'm sorry, this is a Korean language, but this is a note for C.5 cornering. So please look for the counterpart of English version, note, C.5 note. And datum A, the perpendicularity, geometric tolerance, and H7, dimensional tolerance is given, okay. Pi 16, H7, the dimensional tolerance, okay. So even if it is by using CAD tools, the thick and thin line has to be maintained. Thickness is very important, okay, and geometric tolerance and tighter space, okay. And what is it? Surface roughness. Surface roughness. So it's 0.6 is given. So there is no specific surface roughness is designated, but by this placing, surface roughness placing, you see, all surfaces has to be machined with the surface roughness of 1.6. Okay, 1.6. So it should be done by grinding, maybe. Not, it's not lathe and general milling. Maybe 1.6 surface roughness would be impossible. All right. Okay. This has been the whole lectures on the principles of product drawing. Okay. And also there is some appendix for you, which is a Korean language, though. That is would be very helpful for you to design your job career in your future. So, okay. All right. Thanks so much.